Questions about anything from last time? Or about anything? Well, I told you that I needed that calculus lemma, and I assumed it and finished off the demonstration of the Cauchy Riemann equations. That when the u and v are C1 smooth and satisfy the Cauchy Riemann equations, then u plus iv defines an analytic function. That's exciting news. Of course, that's on an open set. They have to be C1 smooth on an open set. And I needed this calculus lemma, which is sort of a Taylor's theorem with first order. It's the remainder term for the first order Taylor approximation. So there's the lemma there. I need to assume that u is C1 smooth to get this. And then I write out the first order Taylor polynomial. And then I have this remainder, r of xy. I want to see how closely that Taylor polynomial approximates u. So I want to show that r goes to 0 so fast that even when I divide by something that also goes to 0, it still goes to 0. Okay, and it's it's an elementary proof that just uses calculus. So I figure I ought to show it to you. It's easier than the general Taylor formula with remainder because it's just the first order term. Anyway, I take a line, the curve, which is a line connecting x0, y0 to xy. And of course, you know how to parameterize that curve from Math 261. Looks like that. And then I'm going to use the fact that u evaluated at the endpoints of those curves, so u at the end minus u at the start, is just a line integral of grad u dot ds. That's something you learn in Math 261. And when I calculate the gradient, well, there it is, gradient u, that's du dx in the first spot, du dy in the second spot, and I'm traveling along that curve, so I put the coordinates of the curve inside those two functions, and I'm going to dot that with ds. And ds for that curve is just the tangent vector dt. And the tangent vector is x minus x naught, comma, y minus y naught. So that's just a calculus thing to write down that integral. And that's a dot product. And so I write it out and get that rather simple looking thing. And you stare at that for a while, and is supposed to be pretty close to the first order approximation. And if you think, boy, that looks like the first order approximation, it's just, what's the difference? The first order approximation, I'll write it underneath here, there it is du dx evaluated at the starting point only, times x minus x naught, plus du dy evaluated at the starting point, times y minus y naught. And that kind of looks like that integral. And when you think about it, that thing there is just a constant, and if I were to integrate it from 0 to 1 dt, it would stay the same. So in fact, I see, those things are very similar to write out as integrals. So I look at those two integrals and realize now that if I subtract them, that subtraction is exactly the remainder. And so I have this nice integral form. This is like the Taylor's theorem with remainder. In integral form. And so it's u sliding along that curve minus u sub x at naught, the starting point. Which, if those things are continuous, the first partials are continuous, by making that little curve short, those can be made as small as I want. So, in thinking about estimating that error, that first thing, u sub x minus u sub x evaluated at the naught end, I can make that as small because of continuity of the first order partial derivatives. And so that max, give me an epsilon bigger than 0, I could choose the endpoint within a delta so that that max of u sub x minus u sub x at the starting point is less than epsilon over 2. Okay. Same for the y term. I can take the delta to be the minimum of the two that would make those less than epsilon over 2. And then when I stare at that for a minute, if I divide that by the square root, then see in the second spot there, that y minus y naught is the leg of that triangle, and the square root is the hypotenuse. So that thing in the numerator is just the leg divided by the hypotenuse. That's less than or equal to 1, because the leg is less than or equal to the hypotenuse. And so when I estimate those two things, I get epsilon over 2 times 1 plus epsilon over 2 times 1. That is epsilon. So I wanted to have that out there. Kind of went through it fast, and you ought to sit down and look at it and say, yeah, I believe that. Anyway, that's a proof. Questions about that? It's just calculus. Which a lot of this subject is just calculus. And when it's not just calculus, it's calculus with complex numbers. Oops, what happened there? Okay, so now that we've got the Cauchy Riemann equations in the bag, here's some exciting things. I'll call them exciting consequence. Here's one exciting consequence of the Cauchy Riemann equations. If u and v are two smooth functions that satisfy the Cauchy Riemann equations, so we've got u and v are twice continuously differentiable. C2 smooth, real valued, functions on R2 that satisfy the Cauchy Riemann equations. Which means u plus iv is analytic. Of course, there's an open set in the background. Then the u and v are harmonic functions. And this is one of the fantastic reasons that complex analysis is important. And the demonstration is going to be quite simple. We're going to do the Cauchy Riemann equations twice. Why? So let's see. We would have the Cauchy Riemann equations. Du dx equals dv dy. And du dy equals minus dv dx. Let's call that first equation A and the second equation B. Okay, so here's the trick. I'm going to take d by dx of A. That's going to give me du dx dx equals dv dx dy. And then I'm going to take d by dy of B. That would give me du dy dy equals minus dv dy dx. Okay, we know that V is C2 smooth. C2 smooth, and therefore those mixed partials are equal. Vxy equals Vyx. That's important. And that's the key here. And so when I add these two, well, let's see what I'm going to do. Yeah, I'm going to add them together. I'll take a plus here, and I would get du dx dx plus du dy dy equals, those things cancel because those mixed partials are equal, and I've got a plus 1 and a minus 1. So that's a big fat 0 here. So check, u is harmonic. And similarly, we can do the same thing with v. I won't write out as carefully this time, but similarly, using that u is C2 smooth, we can say, I think this time you would take d by dy of A and subtract d by dx of B. And look at the right-hand side. That is going to give you the Laplacian on the right-hand side, and that shows that V is harmonic. So that's all there is to that. I mentioned this big fact last time. Namely that F analytic implies F prime analytic. Which of course implies that F double prime is analytic, etc., etc. Okay, that's kind of an advanced fact that's more philosophical importance than something you use on a daily basis. So it's the kind of thing we're going to skip in this first class. I do it very carefully in the graduate version of this class. It takes 3 lectures usually. It's kind of a beautiful math question.
I don't think I fully understand how you show that V is also harmonic. You talk about the Laplacian.
Let's see. When I take d by dy of the A and look at this, the right-hand side, that would be dv dy dy. And then when I take d by dx of the B, look at the right-hand side, that would minus dv dx dx. And so when I subtract that, I get the Laplacian on the right. And I'd use the equality of the mixed partials of u to see that it's harmonic. So it's a very similar calculation to the one above. Anyway, so this big fact, which I'm not going to dwell on in this course, implies that the U and the V are actually C infinity smooth. So the U and the V are always harmonic. So F analytic implies U and V are harmonic. And of course, harmonic functions come up in steady state temperature and electrostatics and all kinds of places in science and engineering. And in fact, one of the great things about these harmonic functions U and V, so that's a big fact. Maybe I'll call this big facts. Here's a fact I can show you. So that's a big fact. here's a great fact I can show you. Namely, the level sets of U and V are orthogonal. Level sets of U and V are orthogonal. They cross at right angles. Let's think about that. I'll make two level sets that cross at right angles here. Let's suppose this is V of xy equals k. And here's another level set of the U. Let's suppose this is, that looks like a right angle, U of xy equals c. Well, you learned in Math 261 that the normal vector to a level set is the gradient. So the gradient of the V is orthogonal to the curve. That's the normal vector. Similarly, the normal vector to the other one would be the gradient. It doesn't look like a right angle. That's more like it. That's the gradient of U, are the normal vectors. To the level set. Okay. And what I want to show is this angle that they cross. That would be the angle those curves cross. I want to show that's a right angle. And the calculation is pretty straightforward. Let's see. I want to take grad U dot grad V. And grad U is du dx, du dy, dotted with dv dx, dv dy. And that's du dx, dv dx, plus du dy, dv dy. And of course, now I'm thinking about Cauchy Riemann equations. Let's see, I'll only apply the Cauchy Riemann equations to the U function. Then I'll get only V's there, and that's going to make it 0. Let's see, remember, du dx is equal to dv dy. And du dy is equal to minus dv dx. Those are the Cauchy Riemann equations. I'm only applying it to the U function. And that's all it takes. Now I get plus something minus something. And that's a big fat 0. So sure enough, those normal vectors are orthogonal. So of course the tangent vectors are orthogonal too. So the normal vectors being orthogonal implies the tangent vectors are too. So that's that. And if you've ever looked at physics book on electrostatics, and you'll see that the lines of equipotential are one thing, and the field lines are orthogonal to them. Yeah.
What's a level set?
A level set is so the level set of the function u is where u of xy is a constant. So if you're thinking about the temperature in Indiana and it's 70 degrees in Lafayette, if you look at the level set of where it's 70 degrees, that would be a isothermal level set kind of thing. So, for example, that would be, in the case of electrostatics, the U might be constant potential. And the V might be a field line following their nose along the field. And those things are orthogonal. And so very often those big, beautiful pictures, especially in 2 dimensions, are actually, there's an analytic function in the background, and these turn out to be the level sets of U and V. So in fact, if you take an engineering class, they might use complex analysis to solve some of these problems, especially in 2-dimensional fluid flow and things like that. The Joukowsky airfoil is a beautiful example of complex analysis applied to engineering. Questions about this fact? Well, this leads to a natural question. We're starting to understand there's a relationship between harmonic functions and analytic functions. If something's analytic, then its real and imaginary parts are harmonic. And you might ask a question. Given a C2 smooth harmonic function, can I find a V so that U plus IV is analytic? A V such that U plus IV is analytic. The answer is going to be yes on regions with no holes. So we'll see in a minute. Yes, on open sets with no holes. Holes are always a problem. We'll see why soon. Okay, so let's think about it. Yeah.
So we said that for analytic, then after analytic, then you would be on harmonic, but we also go the other way.
Right, so we start with one harmonic function. We want to know if we can get another one so that U plus IV is actually analytic. That would give us the relationship between the two more vividly. And in fact, being a harmonic is going to be equivalent to locally being the real part of an analytic function, period. So let's see. Let's think about this. Given U, I want a V that satisfies the Cauchy Riemann equations. V with Cauchy Riemann equations. du dx equals dv dy, and du dy equals minus dv dx. Okay. And I look at those and I realize, here's what I want. I'll put this one up here. I want dv dx equals minus this given thing, du dy. And this one tells me I want dv dy equal this given thing, du dx. So these things are given here. And that's a very familiar problem in calculus, physics, and you name it. I'm looking for a function. Let's see, I want a function that has a certain gradient. So if I'm going to solve this problem, I want a V with grad V equals F, force field. Think of force field, where F equals, let's make it a vector, minus du dy, du dx. V is a potential. Want a potential function. it's called a potential function, V, for the force field F, or whatever kind of field it is. Well, that's a well-known problem in physics and science. And the famous thing in R3, if this were gravitation, in order to solve that problem, I would need the curl of that thing to be 0, curl of the vector field. In order to get the V. And in that, yeah, I'd also have to worry about weird topology like holes in R3. But you would have seen examples in Math 261, what goes wrong when there's a hole. And in R2, which is where we are, there's kind of a curl thing in the background, but here's how it's easy to think about it. Okay, if we had such a potential function, so I have grad phi is equal to d phi dx, d phi dy, and if that was equal to first component of f, second component of f, then we know, let's see, if this thing is C2 smooth, we would know the mixed partials are equal. So d phi dy dx equals d phi dx dy. So let's see, this is d by dy. D phi dx, let's see, that's d by dy of d phi by dx. And this is d by dx of d phi by dy. This one's F1. This one's F2. And so if this thing does have a solution, it has to be the case that F satisfies this condition. I'll put it in a box. So we see easily that this is a necessary condition, that d by dy of F1 equals d by dx of F2. So it's very straightforward to see that that's a necessary condition. To get a potential. Well, in Math 262, you spend a week or so showing that on something that doesn't have a hole, that's also sufficient. Math 261, that condition is also sufficient. In domains without holes. Going around a hole is problematic. Let's see if we have it in our case. Which I'll call this star. So the question is, do we have star? Let's see, remember F1, let's see, F, what was the F? I got to go look at it. First component is minus du dy, second component is du dx. So there's F1 and F2. And now if I calculate d by dy of F1 is minus uy, is that equal to d by dx of F2? And the answer is yes, because that's the Laplacian. Because du dx dx plus du dy dy is 0. So, yeah, because u is harmonic, that's exactly what we need for that condition to hold. And so then we can find the v. So we can find v. Okay, and you go back to Math 261 and see how you did that. I'll show you some examples just to refresh your memory. Let's do this example. Du dx dy, I'm not saying, u of xy is equal to, how about x squared minus v squared plus xy plus 3. Okay. Trust me, that thing's harmonic, but you should always check. Check. Laplacian is identically 0. I'll pretend I checked that. And now I'm going to find a v with dv dx, dv dy. Remember those two equations I swapped? That's minus du dy. And so now I'll take that derivative. Derivative of the, I guess I should write it out. That's minus d by dy of x squared minus y squared plus xy plus 3. And that's 2y minus x. And dv dy is du dx. And du dx is 2x plus y. Let's call this top equation A and this bottom equation B. Let me write them again just to make it cleaner. Here's A. dv dx is 2y minus x. And B is dv dy equals 2x plus y. Now here's a step-by-step recipe. This is true on the whole plane. So of course there's no holes. Don't have to worry about holes at all. Step 1 is use A. Okay, and here's the way I like to do this. I'm going to use some. You'll never see this notation in the book. I invented this notation myself. That's a partial integral sign. A curly integral sign means I'm going to integrate the function there, 2y minus x, with respect to x. So dv dx is supposed to be that thing on the right. I'm going to treat y like a constant in this calculation. So I call this a partial integral with respect to x. And this means treat the other variables like a constant. Treat y's like constants. That's what my funky symbol means. And so I like to, no one's going to call this a partial integral. Except me. That's just to help you remember what you do here. And then so I do that, and let's see, so y acts like a constant, so that's going to be 2y constant times x minus x squared over 2. And now here's an interesting thing. Normally we'd say plus c. But because y is floating around, this c might be different for different y's. And so this c is actually an arbitrary constant of the other variable. An arbitrary function of y, which is the other variable in the partial integration. Okay. And I get, or I should say I got, v, I'll clean it up a little bit, is 2xy minus 1/2 x squared plus an arbitrary function of y. I'll put that in a box. That's quite a lot to get. And now I've used up a. I'm done with a. I can't squeeze anything more out of a. And now step 2 is I'm going to use b, but I'm not going to do it in the same way. So step 2, use b, but in a different way. I'm not going to do the integral routine. Okay, so remember what b was. B was dv dy equals 2x plus y. Okay, well I've got v pretty much figured out above. And so v is that from that red box means I take d by dy of the thing in the red box. The thing in the red box is 2xy minus 1/2 x squared plus c of y. And I want that to be equal to 2x plus y. Okay, let's calculate that. d by dy of that thing is 2 times x minus 0. And partial derivative of a function of y with respect to y is just the ordinary derivative, c prime of y. And it looks like, oh my gosh, I got functions of x and functions of y here. And I'm trying to solve for that derivative of c prime. But a miracle happens, and it happens exactly because of the harmonic condition. All x's cancel at this point. If they don't, you screwed up, or maybe u was not harmonic. If they don't, you made an error. And maybe the error was that u wasn't harmonic. So I'll put that in parentheses. Or maybe, if you didn't make an error, then maybe u wasn't actually harmonic. But that would doom this to failure. Okay, so note all those x's cancel out, and I'm left with c prime of y equals y. One variable, simple thing to deal with. And you see that that c of y would be the integral of y dy. And this is a regular one variable thing, so that would be 1/2 y squared plus a constant. And now you think you're done. We are done. But this is where people screw up, because they go back and they look at the equation above. That's an equation for dv dy. you got to keep scrolling back until you find the red box with V in it. We just figured out what C is. C of y is. And there's V. And so we go back to that red box and put the C of y in there. So it's so we go back to the box that had a V equals ... plus C of y in it, and fill in the C of y. And when we do that, we get that V is equal to, what is it? 2xy minus 1/2 x squared plus 1/2 y squared plus k. Okay, this right here is the C of y. And a nice fact is that harmonic conjugates are unique up to the addition of an arbitrary constant. So here's a fact. Did I say the word harmonic conjugate? I'm going to say it in a minute. So a definition is V is called a harmonic conjugate. V is a harmonic conjugate. For U. It's the thing that makes U plus IV analytic. And they're unique up to the addition of a constant. V is unique up to addition of a constant. Got a few minutes to think a little bit more about this. If I would kind of want to write my analytic function as a function of Z. So U plus IV is analytic. How would I go about writing it out as a function of Z? And here's a rather simple way to go about doing that. Let's see, Z is x plus IY. Z conjugate is x minus IY. And so I can solve for x here like I did in the sine and cosine business and get that x is Z plus Z bar over 2. And y is Z minus Z bar divided by 2I. And now if I go back and plug those into my function, plug in, I won't actually do it, but I would plug it into the U plus IV above. A miracle happens, all the Z bars cancel. So it's kind of like the same miracle that happened. The miracle, all the Z bars cancel out, leaving a function of Z. It's a polynomial in Z. So if somebody locked your room and said, don't come out until you can get that as a function of Z, that's the straightforward way to do it. Let's see, I've got a few minutes here. I was reviewing some stuff you would have seen in Math 261, and one of them was that thing about the partial integral. Let me say a little bit more about why the C is a C of y, an arbitrary function of y. So it's a simple fact that if dv dx is identically 0, then v is a function of y. Alone. And that's an easy thing to see. So let's see, I'll draw a picture here. Here's my, what does remember what dv dx being 0 means. Dv dx means hold the other variable constant. So we'll hold this y constant. And then we differentiate in the x direction. So dv dx identically 0 means that v is constant along horizontal lines. Okay. So whatever that constant is, I could say, okay, let's call that constant C of y. So it is a function of y. Let me think about it like that. And I should say conversely, if you take d by dx of a C of y, you get 0. So that's kind of an if and only if thing. Okay, so let's think about our v that we calculated. Our v above. My crazy partial integral calculation produced a v with the correct partial derivative. With the partial derivative we wanted it to have. Was that what was that? Was a d by with the d by dvx we wanted it to have. If v twiddle was another one, v twiddle was any other such v, then I would have that its derivative, let's see, d by dx of v minus v twiddle, they'd be the same, so this would be a big fat 0. And that would mean that this thing is a function of the other variable y. By our previous remark. And so any old one, I would get that all possible things here are the one we got by our partial integration baloney plus an arbitrary function of y. So that's maybe the scientific way of seeing why that is required to be a C of y. Okay, so now I've justified that. Any last minute questions about anything? In the exercises, you'll get some chance to do this routine. It gets to be kind of fun after you do it a couple times. Okay.